Alright, welcome to the September 23rd video, and we're going to finish talking about the material of section 11.1 from functions of multiple variables, where we simply introduced the idea of a function of multiple variables as well as its graphs. And then we're going to get started on 11.2, and here we're going to get started on the ideas of what if we took the calculus 1 stuff that we did, limits and derivatives and continuity, optimization and all of that, and what if we tried to apply the ideas of calc 1 for single variable functions to our functions of 2 or 3 variables, for example. So by the end of the day, here's what we should be able to do. First of all, to finish up 11.1, the first thing that we need to be able to do is use the contour map of a function, use its collection of level curves, to estimate a function's output value. Not even looking at the graph, perhaps without even having access to the function's equation, can we estimate its output. Then, getting started talking about limits, we're going to first of all informally define what a limit is for a function of 2 variables. And then we're going to use a theorem called the two-path test to show that a particular limit does not exist. Okay, let's get started. So, here we are given a contour map for a function f of x, y. And we are not given any data about the function's actual equation. Of course, I know what it is because I created the contour map, but you don't know what it is. So let's use the contour map to give a reasonable estimate of the value of f of 2, minus 1. Okay, so looking at this contour map, we have our x-axis and our y-axis. And the first thing that I'm going to try and do is I'm going to try and locate this point x equals 2, y equals negative 1 on this image. So based on the scale here is x equals 2. Here then, based on the square scale, would be y equals negative 2 down at this the bottom of this first box here. So if I go about halfway, then I'm guessing that the point that I'm interested in is roughly speaking right here. Now, look at the position of this point. It is nestled between the level curve corresponding to z equals negative 2. And it is also nestled between that curve and the curve corresponding to z equals negative 1. What that means is the elevation of this point, the output of this point, is going to be between z equals negative 2, the level curve over here on the right, and z equals negative 1. So let's jot that down. Point, let's decrease the font size a bit, point is between z equals negative 2, z equals negative 1, which implies that f of 2, negative 1, that output, is between the output negative 2 and the output negative 1. Now, that is already pretty good information considering that we don't actually have the function's equation. But I think we can even be a little bit more precise than that. Because if I take a close look at this point at 2, minus 1, it appears to be slightly closer to the negative 2 curve than it is to the negative 1 curve. I think that the distance to the negative 2 curve is just a bit smaller than the distance to the negative 1 curve. So let's jot that down as well. Point is closer to z equals negative 1, negative 2 curve. So that implies that the output is closer to negative 2, that associated output. I'm just going to add this term here, curves. All right, so based on that, let's just do an estimation of the function's value here. It's between -2 and -1, a little bit closer to -2 than it is to -1. So I might guess something like f of 2 comma -1, maybe let's say -1.7 would be a reasonable guess based on the data that's available to us. It's closer to -2 than it is to -1, and it's between those two output values. And so this would be my reasonable guess. Now, of course, your guess doesn't have to be exactly the same as mine. This is just an estimate. If you get something like -1.6, -1.8, that's all very reasonable as well, so long as it satisfies these two conclusions based on our observation about these level curves. All right, so that's extremely powerful. Just by looking at the level curves, we can get pretty decent estimates for the output of the function at all the points visible on this contour map. This even without having access to the function's equation. Now, here's an exercise for you at home. I wonder what the graph of this function looks like. If I take the three-dimensional graph, the graph seems to be increasing in height in both the positive and negative y directions, whereas the graph is rather rapidly decreasing in height in both the positive and negative x directions. So just as an exercise, let's think about what the graph might look like. At the center, the graph has an elevation of 0 at the very center, but it decreases in both the positive and negative x directions, and it increases in both the positive and negative y directions. So that's an interesting thing to think about. What kind of shape would create this sort of saddle appearance around 0, 0, where it's going up, or Pringle if you prefer Pringles to saddles, that it goes down in one direction and up in another. Now that more or less concludes section 11.1, and with that said, we're going to move on from 11.1 to section 11.2 so that we can get started talking about limits. Now the notation for limits of multivariable functions is extremely similar to the notation for limits of single variable functions. We have the letters LIM, short for limit, and underneath that we have the point x comma y approaching the point a comma b. So instead of x goes to a, x and y go to a and b respectively. Next to the limit symbol, we have the function itself, f of xy, and that is equal to some number called L on the right-hand side. This is read the limit of f of xy as xy approaches ab. That equals L if the following condition is satisfied. If letting the point xy get close to AB causes the output f of xy to get closer and closer to the output L. Now, one of the essential things about limits is that all that matters is what's happening close to the point AB, in the neighborhood, in the vicinity around AB. The actual value of f of AB itself does not matter. What is happening at AB does not matter. All that matters is what's happening near AB, just as with single variable functions. You could have a hole at that point. The point could be floating, it could be moved somewhere else. Who knows? But what is happening at the point doesn't matter. The only thing that matters is what's happening near the point. Alright, so let's consider the following function. Take the function with the equation f of xy equals the square root of 9 minus x squared minus y squared. Now from that function, I'm going to create a new function which I will call g of x. And I'm going to get that new function by modifying the old function f in the following way. All I'm going to do is I'm going to restrict the domain of f of xy. I'm going to artificially restrict it just like we artificially restricted the domain of sine of x in order to get its inverse. I'm going to restrict the domain of f of xy, and I'm just going to delete the point 0, 0. And in terms of the graph, this is equivalent to taking the graph of xy and just poking a hole right in the north pole at 0, 0, 3. So let's get a very rough sketch going. Here I'm going to graph f of xy, and this is going to be a hemisphere of radius 3, similar to the hemisphere of radius 2 that we graphed in the previous video. And then our graph of g of xy, which is exactly the same, except I have come in with my needle and I have created a hole right here at the very top, and I've just deleted that point. Now, let's consider what happens to the output of these functions as we get closer and closer to the point 0, 0 is what this should be saying. xy approaching 0, 0. Now, as xy approaches the point 0, 0, climbing up this hill toward the crest, toward the North Pole, the output is getting closer and closer to the z value at that North Pole, which is equal to 3. The radius of the sphere is the z value that's achieved at the North Pole. So the limit of f of xy as xy approaches the North Pole is the output of 3. Now, if someone asks me to plug 0, 0 into the function f of xy, plugging x equals 0 and y equals 0 into this formula will give me the square root of 9, which is also 3. So for this particular function f, the limit agrees with the output of the function at the point. Now let's go over here and look at g of xy. Once again, if we try and climb up the hill and we try and approach the point xy equals 0, 0, if we approach the North Pole, as we get closer and closer to the hole, the output is still approaching this z value of 3. But what's different here is that if I try to plug 0, 0 into the function g, the result will be undefined because we removed 0, 0 from the domain of g of x, y. So just as with functions of one variable, a hole in the graph, or the removal of a single point from the domain of a function, doesn't affect the limit. It only affects the output of the function at that point. The limit doesn't care what's happening at the point. It's only caring about what happens around the point, just as with single variable calculus. Now, in single variable calculus land, we had a relatively simple criterion to decide whether the limit at a point existed or not. And that was to consider what happened if we approached the value from all possible directions. To approach it from the left, to approach it from the right. if I got a consistent limit from both the left and the right-hand side, then we said that the limit existed. But if there was a discrepancy between the output that we got from the left-hand side and the right-hand side, then we say that the limit doesn't exist. Now, when we're dealing with functions of multiple variables, this idea becomes instantly more complicated. So let me just put in a thought bubble here. xy can approach AB from infinite directions. You can have your graph, you can have your point AB, and potentially xy is approaching it from the top right, or maybe from the bottom right, or maybe directly from the left, or everything in between. So in order to make sure that the limit exists, we must approach the same value no matter what direction you approach from. Not just left and right, but also, northwest, north-northwest, west, and any combination you can think of in terms of directions. So the two-path test enters as a way to quickly tell if a limit does not exist. This is a thought bubble. The two-path test says if you can let xy approach AB along two different paths, and get two different outcomes, the limit definitely cannot exist. If I approach the point AB from the top right, and then I approach the point AB from the left, and those two different approaches give me two different outputs for my function, the limit definitely cannot exist. You know for sure the limit does not exist. Now, just as a point of warning, when it comes to limits for functions of two variables, it is very, very difficult to show that a limit actually does exist. It is very difficult to show a limit does exist. So, in order to show that a limit does not exist, all that you need to do is find two different paths along which the function approaches two different outcomes. If you want to show that a limit does exist, you have got to show that you can approach the point AB along any possible path and get exactly the same outcome. Now, notice that you can't actually show this by plugging in all possible approaches of xy to AB, because there are infinitely many. You cannot show a limit exists by showing that the output is the same as xy approaches AB along many paths. Because no matter how many paths you test, I am going to be able to come up with a path that you haven't tested, because there are infinitely many possible ways for xy to approach AB. Not just straight line paths, but also curved paths. Let's just suppose that AB is on the origin. You can come in and you can approach along the line. Let's say that this line is y is equal to 3x. Maybe the output is what you want along this line. But then someone else comes along and approaches along the line y equals negative 3x. Gets the same answer. So far, so good. But you can approach along a curved path. You can approach along the path y equals x cubed. And that would also have to give you the exact same output. And you can just keep testing and testing individual paths, but you'll never be able to test the full collection of paths that are out there. So it's easy to prove that a limit does not exist. It's very, very difficult to show that a limit does exist. And we'll have to talk tomorrow about a very limited collection of techniques to show that limits actually do exist. Okay, let's get a concrete example going. Let's show that this limit doesn't exist. Okay, now the idea is to choose two different ways for xy to get closer to 0, 0. And show that the function approaches different values along those two paths. Again, we're showing that the limit doesn't exist. So this is the easy one. All we have to do is find two different paths of approach which give us different outputs from the function. Now, often this is a trial and error kind of thing. I tend to like to draw the xy plane over on the right hand side. And I will position 0, 0 here in the center, and I will consider some different ways that I can cut in and approach this point. For example, one way to approach this point would be directly from the east, along the path y equals 0. Along the path y equals 0 is one way to get in toward the point 0, 0. Now let's look upstairs and let's consider what would happen if I approached along the path where y was equal to 0. If I set y equals 0 in the formula for the function, then the numerator is 0, the denominator is non-zero, and so this is equal to 0, and the function's output value approaches 0 as we approach 0, 0 from this particular direction. Now, next, maybe I'll choose another method of approach which has a slight slant to it. Maybe I'll come in at an angle along the line y equals x. Let's see what happens as I approach x equals 0 along the line y equals x. So I'm going to go into my function and I'm going to put in the data that I get from this path, that along this path y is equal to x. So here I go, y is equal to x, so xy can become x squared, and x squared plus y squared can become x squared plus x squared. Now if I simplify that, then this tells me that along this entire path where x is equal to y, the function's value is equal to 1/2. 1/2, which is not equal to the 0 which I got from the other method of approach. So then I can conclude the following. The function's value is different as we approach 0, 0 along the two paths. The first one was y equals 0, and the second one was y equals x. Since we got a different value from these two different paths, we can conclude by the two-path test function's limit does not exist. Okay, once again, I can't encourage you enough to be careful and never ever use the two-path test to try and show that a limit does exist. This is similar in nature to the divergence test from Calculus 3 when you were studying series. It was very easy to show that a series diverged using the divergence test. But in order to show that a series converged, you need all these other ratio test, root test, integral test, all of this other stuff, because it was harder to show that a series converges than it was to show that a series diverges. And again, it's the same situation here. Very easy to show that a limit does not exist. Hard to show that a limit does exist. Practically impossible except with a few key algebra tricks, which we'll talk about tomorrow.